we in the last lecture we implemented this AB plus CD whole bar with the use of NOR gate. Can we implement using the? Can you try to implement using the NAND gate? Can you try? What is how to implement the NAND gate? We know that AB whole bar is equal to A bar B bar. So A bar plus B bar. So we have to make this expression in such we have to simplify this expression in this way, so that we can use this and you can implement that expression in terms of the NAND gate. Can you try this? We have to just you apply the rules, some Boolean expression theorems like the De Morgan theorem and the complement of the complement is that variable itself. Okay, so we have to apply these two things only. Can you try using the NAND gate?
Yes, ma'am.
Okay, ma'am.
Oh, try. Here, what will be the difference? The only difference here with the previous one is A plus in the NOR implementation. What we do, we complement this. Okay, in the NAND implementation, we complement the product terms. Okay, so what we have to do, individual term, we have to apply this theorem. Okay, this is the difference. So instead of complement the whole expression, you have to complement and double complement the individual product terms. This is the difference. Try to simplify in terms of the NAND gate and tell me how many number of NAND gates are required to implement this A plus BD whole bar. Try and tell me how many number of NAND gates are required to implement this A plus CD, AB plus CD whole bar.
4, ma'am.
4? Sure. Try.
Yeah, I tried. I got something.
Okay. Okay, let's see. This is the AB plus CD whole bar. Okay. So here what we have to do, we have to apply here AB bar. Okay. So this will be same. So individually we will apply this theorem. So A bar plus B bar whole bar. Okay, and CD is C bar plus D bar. So what we got here, this is the this was the expression. Inside that expression we got A bar, B bar, this plus C bar, D bar, and this one. Now tell me how many number of NAND gates are required. See, suppose this is the one term. Okay, Suppose this is assume this is x, this is y. Okay, the whole bar is this. Here one more bar, here one more bar, and this will be become x and y with plus between these. Okay, so what will happen here? We need this term makes one NAND gate, but the expression includes the complement of the NAND gate. Okay, so we need here one NAND gate. This, suppose this is x and this is y. Okay, now what are here x and y? Here x and y are a bar plus b bar. Okay, and y are c bar plus d bar. Okay, so for this x will be what? Here only one. This is a, b, and here cd will be same. So it will go here. So now the ultimate expression is what? This x bar plus y bar up to this. Okay, so suppose this is z. So z, the last the final expression is z bar. So here one more, we need one more NAND gate to complete this implementation. So the final will be, expression will be this one. Okay, the capital. So now how many number of NAND gates are required here? 1, 2, 3, 4. It's 4 number of NAND gates are required. Okay, clear? Everyone clear?
Yes, ma'am.
Okay, so for this, okay, try to implement this same AC plus BC dash in terms of the NAND gate, and tell me how many number of NAND gates are required for this implementation.
This only we did first now.
You have to implement this one, this AC plus BC dash in terms of the NAND gate. We did
Oh, NAND.
non-implementation for this expression. Now you have to implement this with the NAND gate.
Okay.
Okay. How many number of NAND gates are required? You tell me then.
Have to see, ma'am.
Okay. See. And everyone, please put your roll number in the chat box.
Ma'am, 4 NAND gate.
4 NAND gates. Anyone else? Anyone else tried?
1, 3.
4 9 yes, ma'am.
1062. Roll number 1062. Tell me.
4, ma'am.
4. Okay. Anyone else? 1051. How many number of NAND gates are required here?
4, ma'am.
4. Okay. So I think it's clear to you all that how to implement. So, see. AC plus BC dash. What we have to do? We just need to, yeah, you can visualize actually in the last example a bar was there, so it is not required. Okay, and instead of D here it is C, so we need one NAND gate to implement this C dash, and there will be one less number. In the previous example there was a bar there, so we will not require the last NAND gates here, so extra NAND gate is included for the C dash, and NAND gate is excluded, deducted from for this. So that's why only 4. Do I need to explain this? Okay. Then I will explain what we are doing. Here AC plus BC dash, AC plus BC dash, yeah, or bar. So what we have to do, individual terms, we have to take the bar. Okay. So here what it will implement, the A bar plus B bar, C bar, sorry. This will be A bar C bar plus B bar plus C, here the whole bar, here the whole bar. So here this three this, if we consider these thing as the X and Y, so here we will require one NAND gate. Okay, it require a NAND gate. Here this X is equal to A bar plus C bar, so this will require one NAND gate. Okay, then here it will require this Y, this will also require one NAND gate. But here what is the input here? Here input is B, here input C dash. So to implement this C dash we require one NAND gate. So how many number of NAND gates? 4 number of NAND gates we need here to implement this Boolean expression. Okay, so okay, this is a simple. These were the two. Those were two simple examples to implement any kind of Boolean expression. So these are the the basic. There are three basic logic gates, two universal gates. What are other types of gates we need in the digital electronics? Any idea about the other than these 5 gates? Any idea what are the different gates are there? Exclusive OR and exclusive NOR gate. What are these gates? Exclusive, X, OR, and X, NOR. So this is called exclusive OR It's called exclusive OR, and this another one is the exclusive NOR. So we will in because there are what we do, what is the use of these different boolean these different logic gates, is that we implement some logic. Okay, why we implement those logics, we design those logic, because we need our various applications requires those logics to be implemented. Okay, for our different applications. So those applications involve so many things, like we need to transmit some data, or we want to do some mathematical calculation, whether we use in our calculator or in our mobile phone, or in our microprocessor, anything, anywhere we will use those logics for certain kind of application, or to fulfill or to accomplish certain kind of task. So in those while doing those things, what we require, sometimes we need that when the data is coming, we require that we try to check, compare some data, whether those two data or three data or four data, whatever number of data are coming. Sometimes we require that we want to check those data, whether they are equal or not. To get that information, we require some logic, or some gates, or some devices, so that we can find out whether that those inputs, or whatever things are coming, those are comparable, and those are comparable, then whether they are equal or not. To do that thing, in the further lecture, when we will see the error detection and the corrections, and we will utilize this comparison and then equality logic. So to find out that those incoming data are equal or not, we required some gates. So the exclusive OR gate is the one gate which which tells about whether the incoming stream of bits, actually when we work in the digital domain, we design each and everything, we in terms of some combination of the, or stream of some ones and zeros. So in terms of the ones and zeros, the comparison or whatever tasks are there, they everything will be done in terms of the streams of ones and zeros. So if we want to compare something, that will also done with those ones, combination of ones and zeros. So to find out whether those incoming data are equal or not, we require some gate. So exclusive OR gate is the gate which indicates that thing. If the incoming data are not equal, okay, so then exclusive OR gate will become high. Okay, this shows it means if the incoming data are not same. Okay, if not same in the sense whether it is 00 or 11, 00 is the same, 11 is the same. So for that thing, this this exclusive OR gate will be 0. Okay, now because inputs are 2 here, so combinations will be 4, 0 1 1 0 and 1 1. So according to this, exclusive OR indicates that when the incoming bits are unequal, then it will be true or high. If it is same, then it will be 0. Okay, so if we want to compare something and we want to see the incoming stream of bits are equal or not, are same or not, so bit by bit it will check and it will see these two things are same or not. So if it is same, then the output will be 0 or high, 0 or false. And if the incoming bits are unequal, then it will be high. Okay, so this is the exclusive OR. So the here the symbol is like this. Suppose this is A and this is B, so this will be the XOR symbol, and this is also indicated by this. So this is the exclusive OR symbol. What is exclusive NOR? This is the complement of the exclusive OR is the exclusive NOR. So when the incoming bits are same, then it will be high. When the incoming bits are not same, then it will be 0. Okay, so the symbolic representation is the same with the, because this is the NOT of exclusive OR is the exclusive NOR. Okay, so this, suppose this is A, this is B, so it will become A exclusive is B bar, or this will be B. So this will become, this is the symbol for this one, this, and symbol for this, this is for the exclusive OR, and this is for the exclusive NOR. Okay, so this is the simple, these are the different simple logic gates. We have considered the exclusive OR and exclusive NOR too. So difference between these things are exclusive OR, when the inputs are different, then exclusive OR will give high value, and when the inputs are same, it will give low value. Okay, so the logical expression is, if we try to solve this, that truth table, it will become A B bar plus A bar B. Okay, so this is the expression for exclusive OR. And for the exclusive NOR, if we complement this, so it will become AB plus A bar B bar. So now can you try to implement exclusive OR and exclusive NOR with the help of NAND and NOR? This is also the case, because we say that universal gates are the gates by which any kind of gates or any kind of Boolean expression we can implement. Okay, so this is also the case. This is exclusive OR and exclusive NOR are also the gates, which are the logic function actually, which we indicated here in terms of the gates. So if we want some comparison thing and we want to implement those with the use of universal gates, so we should know that those what the comparison purpose, whether we use exclusive or exclusive NOR, we should know how to implement with the use of NOR and NAND. So this is your task. You have to implement this exclusive OR and exclusive NOR gate with the help of NAND and NOR. Okay, so here from the first unit we have completed the implementation of Boolean expression using universal gates, and next, the last topic from the unit first is the error detection and the error correction. So what is the meaning of this error detection and error correction? What happens, whatever we are doing here, whatever logic we are implementing, what we are simplifying and using k-map or the tabulation method, after doing all these things, we are doing to accomplish a certain task and to for the certain application, or to transmit our data from one side to another side. Okay, so in sometimes what happens, we need to keep the information for longer duration. When we see in the memory section, we will see that there are different types of memory. There's a static or dynamic memory. So the difference between these things is that if the data is retained for the longer duration time, and after certain time, what happens, some data get distorted or lost. So here, when the data is transmitting or data is stored somewhere, and after certain time we track that data, what happens, we find out that the data is lost, or after transmission of that data in form in here in we are talking about the digital domain. So while transmitting that data, what happens, because the data is transmitted using, if the long distance it covers longer distance. So while it travel a longer distance from with the use of certain medium. So the medium can be anything, like if we say it is wireless communication, so the medium will be air. So while when it go around the air, some noise, some glitches will make changes in the valid data. So what happens, certain bits, whether it is if the with a very valid data contains at some certain positions 0, it will convert into 1, or if the valid data contains 1, it will convert it into 0. So that will be the error message we receive, to make sure that the whatever data received by the receiver is not with the error, it is not distorted. While transmitting data from the transmitter side, what happens, we need to that add, or we need to do something, so that after receiving we can able to detect that error, and we can able to correct that error, so that we will not process the errorful data. Okay, so that is the part of the error detection and correction. So we will see the Hamming code method for the error detection and the correction method in the next lecture. Any doubt?
No, ma'am.
Okay, so in the next lecture we'll see the Hamming code and the parity check method to find for the error detection and the correction.
Thank you, ma'am. Oh, before I could say bye, like I said, thank you.